Alright everybody, in this video we're going to talk about free fall and using the kinematic equations, because remember, as you're going through free fall, or any object goes through free fall, there is a constant acceleration acting on it, and that's the acceleration due to gravity. So here's a first example. It's number 1. A person steps off the end of a 3-meter high diving board and drops to the water below. How long does it take the person to reach the water, and what is the person's speed upon entering the water? So let's look at A. How long does it take the person to reach the water? So we're looking for time. Let's look at what other variables it gives us, because that's how we decide what kinematic equation we're going to use, is seeing what variables are given in the problem. So in this one, we have a distance. We're given the distance from the diving board to the water, and that is 3 meters. We're wanting to know how long, so we're looking for time. And then it doesn't give us any other information in the problem. But remember, when you're dealing with free fall, acceleration due to gravity is always there. So you're always dealing with a 9.81 meters per second squared in the downward direction. And whenever you start to free fall, your initial velocity is 0. You're not moving, and then you begin to free fall. So the initial velocity is 0. So let's look over here where I have it written down. And this is what we have. Distance 3 meters, acceleration due to gravity 9.81 meters per second squared, and velocity is 0 meters per second. And if you notice, I don't have the negative 9.81 meters per second squared written, because gravity is really a magnitude, 9.81 meters per second squared. We put the negative in there if we're dealing with the direction like of Earth, and that matters in a problem. When you're searching for time, you'll end up with a negative, and we're not traveling back in time. We're traveling forward. We're talking about from the time the person stepped off the diving board to the time they reached the water. So we're moving forward with time. So when you're searching for time in a problem, sometimes you'll realize, you'll come to be familiar with these types of problems, and you'll realize when and when not to put in the negative or just use the magnitude of gravity. If you don't, it's no big deal, because you'll get to the answer and it'll be like a negative time, and you'll realize, well, I'm not traveling backwards in time, so I'm just looking for the absolute value of it. So, I didn't mean to show that yet, but this is going to be the kinematic equation we use. I wanted to work it through with you and show you. So let's look back at what we have for kinematic equations. Okay, so here are our kinematic equations. We have to decide which ones to use. Remember, we're given the distance, we know the acceleration, so our givens are distance, accelerations, and initial velocity, and we're looking for time. So this equation does not have distance at all in it, so we won't be using this one. This problem does not have time in it, and so we can't solve for t, so we won't be using this one. But this one has what we need: acceleration, time, and initial velocity, and distance. So we have the factors we need, and we can solve for t, so we'll be using this equation right here. So I'll flip back over. And here we are. It's written out now. And now we're just going to sub in what we know. So this is how we do it. We'll sub in these numbers for these variables. So we know our distance. Our total distance is 3 meters. I think it's actually 3.00 meters. So 3.00 meters for that x. This x, distance initially we haven't moved at all in the y direction. We free fall in the y direction towards Earth. So we haven't moved at all in the y direction, so initially our distance is 0. So I'm just going to leave it out because it's a 0. And 0 plus anything is whatever the other thing was, so this matters none. So we'll just move on to this one, velocity initial times time. Velocity initial is also 0. So anything times 0 is 0, so these both will be 0, so they don't matter in this problem. So we'll just go with this, plus 1/2. So let's just go with 1/2. Acceleration, which is 9.81 meters per second squared towards the center of the Earth, and time squared. We don't know our time. That's what we're solving for. So you have all your values. You don't have the variable time solved for yet, so that's t squared. So we need to go ahead and solve for this, and if you remember back from the beginning of the semester, you did algebraic rearranging to solve for variables, so we need to get t isolated, get t squared by itself. So how are we going to do that? Hopefully you said divide by this product right here, 1/2 times 9.81 meters per second squared. So we'll just take it out step by step on this problem. So 3.00 meters equals, and let's see what 9.81 times 2 is. Let's get this over here so you can see it. And 9.81 times half is 0.5 equals 4.905. So 4.905 meters per second squared times t squared. And now we'll just go ahead and bring this over by dividing. So we'll divide both sides by 4.905 and get t squared by itself. So if you take 3 divided by 4.905, you end up with 0.6116. Since we have 3 sig figs to start the problem with, we'll just keep in 3 sig figs of 0.612, 0.612, and we'll end up with seconds squared. Remember, when we divide, meters will cancel out. So we'll just be left with seconds squared. And we don't want to know our time squared. We want to know the time it takes to reach the water if you jump off a or not jump off, but just step off of a 3-meter diving board. So let's go ahead and get the square root of both of these. Square root both sides, you end up with t. Square root of t squared is t. And this, the square root of that answer right there, square root of that is 0.782. 0.782 seconds. So 0.782 seconds is how long it takes to reach the water if you step off of a 3-meter diving board, the time it takes you to hit the water. All right, now let's look at B real quick. Okay, B says, what is the person's speed on entering the water? So now we want to know the speed of the person entering the water. So you just got to think, what is that speed? What variable is that going to fall under? And remember, if you're talking about speed here, we have an initial velocity of 0 meters per second, so the speed upon entering the water, so as soon as you step off of the 3-meter high platform diving board, that's not, looks like a 3 a.m. Let's go. Alright, this is supposed to be 3 meters, 3.00 meters right there. So if you step off that 3-meter diving board and fall to the water below, your initial, as you step off, is 0 meters per second. We want to know the speed upon entering the water. We know how long it takes now to get to the water, but we don't know the speed. So we'll make that our B problem. So we want to know final velocity. We have all our other variables right here. So let's look over. If you look at the kinematic equations, right here is one set up tailor-made for this problem. Final velocity is already isolated. Here's initial velocity plus the acceleration time to time, and we have all these variables. So this is the easiest one to go with, and that's what we'll do. We'll go with that one right there. So that's right. Velocity equals your initial velocity, your final velocity equals your initial velocity plus acceleration times time. Now let's sub in what we have. We know our final velocity is what we're solving for, so V equals the initial velocity is 0 meters per second plus acceleration times time. So our acceleration is 9.81 meters per second squared, and since we're not solving for time, I'm going to go ahead and use the negative this time because we're heading in a downward direction and we're solving for velocity. And velocity in the upward direction is considered positive and the downward direction is considered negative. Since we're not solving for time, I'm going to go ahead and plug that in. Let me get a little bit over a little bit more so we can see this. And our time. We know our time was 0.782 seconds. So 0.782 seconds. Okay, so we have velocity, the final velocity equals the initial velocity plus the acceleration times time. So this is 0 plus anything is whatever it is. So we're going to go ahead and solve for this right here. Negative 9.81. Negative 9.81 0.81 times 0.782. And that is negative 7.67. Negative 7.67 meters per second, because this second will cancel out with this one. So you'll be left with meters per second as your units. So that is how we solve for our final velocity. So we solved for the time it took to drop off of that diving board, just stepping off and free falling, and then we calculated what speed you would reach, what your final velocity would be as you entered the water. Okay, now that's A and B for number 1. Let's look at number 2 real quick, because it's strictly a conceptual problem. Okay, here it is. You drop a rock from a bridge to the river below. When the rock has fallen 4 meters, you drop a second rock. So you drop one, and then when it reaches 4 meters, you're going to drop a second one. As the rocks continue their free fall, does their separations increase, decrease, or stay the same? This is a conceptual problem. There's no math to figure in, so pause this video for a second, think about it, and then hit play and see if you come up with the right answer. Okay, hopefully you said their distance between the two rocks increases, their separation increases. And the reason that is, sometimes it's easy for a physics student to fall into, well, they both fall at a negative 9.81 meters per second squared as they fall to Earth, and that's true. That is correct. At least you're thinking right there. But if you did not say increase, you're not thinking of the first rock is already moving, and since it already has a velocity, and that velocity is steadily increasing at negative 9.81 meters per second squared, it will always be a higher velocity than the other rock that's falling. The other rock's playing catch-up, but as it plays catch-up, it will always be going slower than the first rock, so the first rock will fall, and as they fall, it will separate itself from that other rock. If that doesn't sound correct, if that just sounds like I just don't understand that, then just ask me about it in class, and I'll do a demonstration on the board for you and show you. But just number 2, just know that the concept behind that is if you drop something, they're going to fall at the same acceleration, but the first object you drop will continually go faster and faster and faster than that first object, because it already had speed to begin with when the other object was dropped. Alright, thank you for watching this video, and hopefully that helped.